Welcome again. In a previous video, we did conditional and joint probabilities. And now it's time to look at total probability and Bayes theorem. We'll start with the total probability and then we'll link it to Bayes theorem. So let's start. Now let's start explaining the total probability. We'll start with looking at the math, then we'll make the physical meaning of what total probability is. So we have a sample space. This sample space is divided into number of events. So this is the sample space. This is our universe. We're going to assume that this is divided into mutually exclusive events, which means events that they don't intersect. B1, B2, B3, B4, and I'm showing some colors here. Those are the events that divide the universe. So we're saying here, given n mutually exclusive events, we call them B sub n, where n goes from 1 to capital N, that divides the universe. Okay, when I say, you can see here we have color match. The red says mutually exclusive. Mathematically, we say that the intersection between any two of these sets is going to be phi, which means they are not intersecting. Of course, for any value of m does not equal to n, because if m equal to n, it means you are comparing the set with itself. So the intersection will be the set itself. Okay, we're just giving the basics. We're saying we have a universe, and this universe is divided into mutually exclusive events B1 up to Bn. Divide the universe means if you take the union of them, you're going to get the universe. So this is just in text, this is in math text, and in math expression. Okay, in that case, the total probability says if you want to find the probability of events A, okay, instead of looking at A, you can take the individual pieces here. You can take A with B1, B2, B3, so you can divide the case A into the smaller non-intersecting sets, and you add these pieces together to get the total probability. So the total probability means I will find the total probability of A by looking at the small pieces where A intersects with the small sets B1 up to Bn. So we're saying here A, the set A, which is shown here, of course it's equal to A intersection with the universe. It's A intersection with the universe. If you intersect, you get again A. But we can replace the universe with the union of all the individual events. And now, using the property, I can take the universe, the union outside, which says that if you want to find the probability of A, if you want to find A, you can divide A into smaller pieces, which is shown here. And then you take the union of these all, you get A. In terms of probability, okay, because they are mutually exclusive, the probability of these is equal to the sum. There is no intersection. So I can say the probability of A equal to the probability of what it equals to here. And I can basically add the probability of A intersection with the blue, with the green, with the orange and red, and so on. And remember that the intersection can be written in terms of conditional. So we can come up with the final statement, which we call the total probability theorem. It says, if you want the probability of A, and we have sets of B, you have a group of B sets which are mutually exclusive, you need to remember this formula. Probability of A is like finding the probability of these individual intersections. You can find it like this, or you can use the definition for the intersection and relate it to the conditional probability. So this is something that you need to remember to be able to solve problems. For the Bayes theorem, what does it say? Now remember that we can write the conditional probability of B given A, as the intersection over the probability of the condition. We can also find the probability of A given B as the probability of the intersection over the probability of the condition. Notes between these two, the red expression here is common. So we can write down, we can say, for example, if I'm going to write the red as probability of A times probability of Bn given A. For the second expression, I can write probability of Bn times probability of A given Bn. Okay, now these two are equal because the red term is the same in both expressions. So because they are equal, I can write the following. I can say the probability of B given A, divide both sides, so I got the following expression. And this is what we call Bayes theorem. So a logical question, so what is there in Bayes theorem? Why do we need it? It allows you to flip the condition. So if somebody give you probability of A given Bn, and what you want is the opposite, you want Bn given A. So using Bayes theorem, we will be able to flip the condition. If one is known and we need the other, we can flip the condition using Bayes theorem. We can also combine Bayes theorem with the total probability theorem. So instead of writing PA as is, we can combine them together. Okay, we can write the following expression. So this is another form of Bayes theorem. The only difference here is we have written probability of A using the total probability. It's probability of being in B1 times the condition, being in B2, B3, B4, and we write all the exhaustive cases. So this is one form for the total probability, and here is another form. Sorry, this is one form for Bayes theorem, and this is the second one. Again, Bayes theorem using total probability. So this is Bayes theorem, and this is Bayes theorem plus total probability. We'll need this. It's usually written in this format because we usually need it to solve problems. So once more, we had today covered the total theorem and the Bayes theorem. So we need to remember the two. Probability of B given A. You can always start with the conditional probability and come up with the expression. Alright, here is a nice example about total probability and Bayes theorem. This is basically an example used in communication. This is a binary symmetric channel. We call it binary channel because we are either sending 0 or 1, and we're going to receive 0 or 1. So we call this, we start by assuming that we'll call this P1. What's P1? It's the probability that we send 1 here. So we have 1 or 0. If you have a perfect channel, you will get, if you send 1, you get 1. If you send 0, you get 0. But because the channel is not perfect and there is probability of making mistakes, there is crossover. Okay, so it could go from here to here, but it also could be sent as 1 and receive as 0. And vice versa, you could be sending 0 and receive 1. Of course, this branch has a higher probability of 0.9, and probability of making error, this is still relatively high, 0.1. Their sum is going to be 1 because you are either sending 1 and receiving 1 or sending 1 and receiving 0. Similarly, for the 0, we send 0, we receive 0 with probability of 0.9, and then 0.1 is where we do a mistake. We call it binary symmetric channel. Binary because we have two possibilities. Symmetric because in this example we have 0.9, 0.9, 0.1, 0.1. If we had here 0.8, for example, and this is automatically going to be 0.2, then it's not going to be symmetric because the upper branch is different than the lower branch. Okay, so this is the basic idea. I have defined the events here on the side. So the events are defined here. B1, B2 through A1, A2. And we are given the following. We are told that the a priori probabilities of getting this B1 or sending 1 is 0.6 before being transmitted. Of course, either you send 1 or 0. So automatically, if this is 0.6, this must be 0.4. We are also given what we call the conditional probability or the transition probability. The probability that you start with B1, given B1, and you end at A1 it's 0.9, and probability of you start at B2, given B2, and then you get at A1, it's going to be 0.1, and so on and so forth. So we have 4 transition probabilities, or what we call 4 conditional probabilities from left to right. So what's required in the question? He's saying find the a posteriori probabilities, which means I want probability of B given A, because what happens in real receivers, it's not that we are given B. In real receivers, what we know is the received. We know what we got is 1 and 0, 1 or 0, and we want to know what was transmitted. So A is given in real communication receiver, and you want to know what's the probability that what was transmitted is B1 or B2, 0 or 1. If I get 1 here, this is something given. A1 is given. So what is the probability that what was transmitted is 1 or 0? We'll do this in the next slide. You can pause the video and try it yourself. Basically, this calls for Bayes theorem because we have one condition given and we want to find the other. So let's start with the first one. What's the probability of B1 given A1? If I write the expression for Bayes theorem, it looks like this. Okay, probability of A1 given B1 times B1. So what do we know and what we don't know? What we know is this term is already known. This is 0.6, so this is not a problem. Probability of A1 given B1, this is 0.9, so this should be no problem. This is given here. So what's the probability of A? Using total theorem, I could get into A from 2 directions, either from this one or from that one. So I should start with B1 and go through the transition. So we can write this like this. So either I start here, so this is with probability of 0.6, and I go through this line, so times 0.9. Or alternatively, I start here, probability of B2, which is 0.4, times this transition, which is 0.1. Right, so if you sum them up, you get 0.58. Okay, so there is 0.58 of the cases, or 58% of the cases, will end up with 1 at the receiver. Now we can find A2 in a similar way. You can start with total probability and find A2, or alternatively you can just subtract, because you either end with 1 or 0. So it would be 1 minus 0.58, which is 0.42. Okay. Now if you want to find the other conditional probabilities, the other a posteriori probabilities, I'm done with this part. I have found A. I'm substituting now. This is, as I said, 0.6, 0.9 in the numerator, and then denominator is 0.58. And the answer is 0.931, which means if you receive 1 here, it's 93% that was what was transmitted was really 1. Of course, now, if somebody says, what's the probability that what was transmitted is 0? So here, we came from other branch. You can easily use your logic that it should be 1 minus this answer. So it's 1 minus 0.931. We need to do the same thing for A2, okay, and find the answer. So what's the probability that if I am receiving A2, if I am receiving 0, what was transmitted is 1, or alternatively, what's the probability of B2 given A2? So please find these two numbers and write your answer in the comments. If you can get this thing right, it means you're doing great. So these are the two things in red that I want you to try to find. And please share your answers. Remember that their sum must equal to 1. So please find these two and write your answer down. If you have a good channel, this number should be relatively high because you don't want to receive 0 unless somebody is transmitting 0. So with this we conclude Bayes theorem and the total probability theorem. Thank you for your attention. There are other examples I advise you to do in the textbook, and whatever textbook we have, Populous or whatever, I would suggest, or Beebles, I'd suggest that you go over the more examples to get used over Bayes theorem. Thank you.